Hello. I hope the course is going well for you. I hope you are keeping to the schedule, doing the lessons, homework, assignments, tests and everything going on time. Remember, if you fall behind, it will be very difficult to make up. If you have any concerns or questions, always contact me. It is very important that you keep in touch with me so that you understand and learn the course properly. All right? I want all of you to learn, appreciate and enjoy this course. It's very important that you enjoy your course in order that it may be useful to you. Okay. In today's lesson, we will discuss another new concept called momentum. What does the word momentum means? It is a word that we very often use. Now, I have a trolley here. Does this trolley has any momentum? Well, at the moment, it doesn't have a momentum. But if I set it in motion, it has a momentum. Now, what does the momentum of a moving object depend on? What are the factors on which the momentum of a moving object depend on? Well, there are two factors. One is the mass of the object, and the second thing is the velocity. It is the combination of these which gives a moving object its momentum. Now tell me, is momentum a vector quantity or a scalar quantity? Well, momentum is a vector quantity. While the trolley is moving forward, if its momentum is positive, when it is coming back, its momentum is negative. All right, let's put this in. So, a moving object has a momentum determined by its mass and velocity. And how do you measure momentum? Momentum is measured as the product of its mass and velocity. We will represent momentum by the uppercase P, and if you measure momentum as the product of mass and velocity, what will be its unit? Mass is measured in kilogram, velocity is measured in meter per second, therefore momentum will be measured in kilogram meter per second. So P equal to m times v kilogram meter per second. And we talked about this. Momentum is a vector quantity. That means when you want to add momenta of different objects, we use the rules for vector addition. Okay, let's consider a car of mass m moving with a velocity v0. What is the momentum of this car? Its mass is m, its velocity is v0, therefore its momentum is m times v0. Let's now apply a force F on this car so that its velocity changes from v0 to vf. Alright, this force F will change the velocity from v0 to vf. And the time taken for that change is delta t. Tell me, what is the new momentum of this car? The new momentum will be its mass times its new velocity. What is the acceleration produced on the car? Acceleration is delta v divided by delta t. Delta v is vf minus v0. And this change in velocity occurred during this change in time delta t. Therefore, the acceleration of the car is vf minus v0 divided by delta t. But you know that f equal to ma. So, if I now replace this a by this quantity, Vf minus V0 over delta t, I can now write F, the force applied on this car, is mass times Vf minus V0 divided by delta T. Now take a moment and look at the numerator quantity and tell me, what does that represent? If I now multiply by m, or distribute that m, it will be m times Vf. What does m times Vf represent? The momentum at this time, or we call it the final momentum. Is that right? M times Vf is the final momentum. What is m times V0? Initial momentum. So this is mVf minus mV0, final momentum minus the initial momentum. The quantity on the numerator actually represents the change in momentum. M times Vf minus V0 represents the change in momentum of the car. So I can replace that numerator m times Vf minus V0 by the quantity delta P. So I have the force acting on the car equal to delta P divided by delta T. What does delta P divided by delta T represents? The rate of change of momentum. So force is a measure of the rate of change of momentum of a moving object. Look at this. We have a new way to measure force. In fact, the definition of force in Newton's Principia is given in terms of the change in momentum. The force acting on an object is a measure of its rate of change of momentum. An important definition. Force is the rate of change of momentum. Let's now obtain a relation connecting kinetic energy and momentum. Tell me, what is the equation for kinetic energy of an object moving with a velocity v? Kinetic energy is 1/2 mv squared. The kinetic energy K of a moving object can be expressed in terms of its momentum, and sometimes it will be very useful to do that in solving problems. Alright, kinetic energy of an object of mass m moving with a velocity v is K equal to 1/2 mv squared. Now, what I have done here is multiply and divide by m. Is that difficult to do? Now watch here, 1/2 mv squared, I multiply and also divide by m. Now why did I do that? Well, to make it a little more user-friendly. Look at this. If you don't want it, this mass and mass get cancelled. But by multiplying the numerator by m, this becomes m times mv squared, become m squared v squared, and the denominator is now 2m. If you don't want it, 1m can be cancelled with another m. We will go back to our original expression, K equal to 1/2 mv squared. But I'm sure you now understand 1/2 mv squared is the same as m squared v squared divided by 2m. What is the advantage of writing like this? Well, m times v is momentum p. Therefore, m squared v squared is the square of the momentum. The numerator is p squared. So, kinetic energy equal to p squared over 2m, where p is the momentum of the moving object. A very important relation. I want you to keep track of that. Okay, let's do a small problem. A 0.5 kilogram ball is thrown in the x direction with a velocity 10 meters per second. It hits the wall and rebounds with the same speed. Well, same speed. If you want to talk in terms of velocity, the velocity of rebound has the same magnitude but opposite in direction. The question is, what is the change in momentum of the ball? Alright, our data is mass of the ball is 0.5 kilogram. Its initial velocity is 10 meters per second. That means the ball comes and hit the wall with this velocity. And after hitting the wall, it rebounds with a velocity exactly opposite, equal and opposite. Vf equal to negative 10 meters per second I. Vi, initial velocity is 10 meters per second I. Vf, the final velocity, is negative 10 meters per second I. Alright, now the initial momentum of the ball is Pi equal to mvi. Is that right? Mass times initial velocity. That will be, mass is 0.5 kilogram. Initial velocity is 10 meters per second I. I hope you now understand this in the x direction. And that is 5 kilogram meter per second I. The initial momentum is 5 kilogram meter per second in the positive x direction. Alright, this is the wall, and look what happened. The ball came, hit the wall and went back. So the initial momentum is 5 kilogram meter per second in the positive x direction. What is the final momentum? The final momentum Pf is mvf, mass times the final velocity. The final velocity is negative 10 meters per second I, and that is negative 5 kilogram meter per second. This is the final momentum. Now tell me, what is the change in momentum? The initial momentum is 5 kilogram meter per second I. The final momentum is negative 5 kilogram meter per second I. What is the change in momentum? What is the definition of change in momentum? Final momentum minus the initial momentum. That is the definition of change in momentum. So change in momentum delta P is Pf minus Pi. I know at least some of you thought in your mind that the change in momentum is zero. Is the change in momentum zero? No. The final momentum is negative 5 kilogram meter per second I, and the initial momentum is 5 kilogram meter per second I. Look at this, final momentum minus the initial momentum, and that gives you negative 10 kilogram meter per second I is the change in momentum. The change in momentum is in the negative x direction, and it is equal to negative 10 kilogram meter per second I. It's very important to understand that concept. Okay. Now, this represents, so the red arrow represents the initial momentum, the green arrow represents the final momentum, and the blue arrow represents delta P, the change in momentum. Alright? Okay, let's try another problem. A 0.5 kilogram ball is thrown against the wall at an angle of 53 degrees as shown on the right. Here is the ball thrown at an angle of 53 degrees. That is the angle 53 degrees. And the velocity, initial velocity, is 10 meters per second. It rebounds with the same speed, means 10 meters per second, at an angle of 53 degrees. Now, it rebounds at 53 degrees as shown in the diagram. This is the velocity of impact, and this is the velocity of rebound. Alright, this time also we need to find the change in momentum of the ball. The difference between this problem and the previous one, in the previous one the momentum was just in one direction, it's a one-dimensional phenomenon, whereas now the momentum is a two-dimensional phenomenon. You can see the momentum is a vector quantity. It has an x component and a y component. So we need to now look at the component form. Okay, let's do that. Now, if this angle is 53 degrees, then this angle will be 127 degrees. Is that right? Okay. Pi drawn from the origin. Now, this problem can be made simpler by drawing both vectors. What are the two vectors? The initial momentum vector and the final momentum vector. Now, if you can draw both vectors from the origin. Now, in order to do that, what all you need to do is translate this vector so that its tail is now on the origin. Now, I'm going to draw that over here. So, where will this vector be drawn? It will now be this vector. You see that? As long as the length and the direction remains the same, these vectors are the same. It is simply translated. So this is the initial vector Pi that makes an angle 53 degrees with the positive x-axis. That means the Pi is the momentum magnitude and 53 degrees is the direction. And the final momentum you can draw at the same position. So this is the final momentum Pf, and what is the angle of the final momentum? The angle of the final momentum is this angle, which is 127 degrees. So you must be very clear there. The initial momentum of magnitude Pi, which we will be calculating shortly, makes an angle 53 degrees with the positive x-axis. The final momentum Pf makes an angle 127 degrees with the positive x-axis. Alright, let's calculate Pi, the magnitude of the initial momentum. Remember, momentum is mass multiplied by velocity. The mass of the ball is 0.5 kilogram. Its initial velocity is 10 meters per second. So Pi, the initial momentum, is 0.5 kilogram times 10 meters per second. That is 5 kilogram meter per second at 53 degrees. Alright, let's write that in the component form. Can you help me do that? Pi is 5 kilogram meter per second at 53 degrees. What are the x and y components of Pi? Pi in the component form is 5 cos 53 degrees I plus 5 sine 53 degrees J. I'm sure this is now familiar to you. Is that right? There is no problem there. 5 cos 53 degrees I, that is the x component. 5 sine 53 degrees J, that is the y component. And now use your calculator to find the value. 5 cos 53 is 3 and 5 sine 53 is 4. So Pi is 3i plus 4j. Now how will I represent that over here? This is 3i and this is 4j. The momentum Pi has the x component 3i and the y component 4j. Similarly, let's write the final momentum in the component form. Pf is 5 kilogram meter per second at 127 degrees. In the component form, it will be, alright, can you write that? It will be 5 cos 127 degrees I plus 5 sine 127 degrees J. And using the values of cos 127 and sine 127, you get it as negative 3i plus 4j. The x component of this is negative 3i and the y component is 4j. And now, we have now broken these vectors into their x component and y component. Therefore, we can now find the change in momentum along the x direction and the change in momentum along the y direction. Alright, let's see how many of you have been following my argument. Tell me, what is the change in momentum in the y direction? What is the change in momentum in the y direction? Well, there is no change. Initial y momentum is 4j. The final y momentum also is 4j. There is no change. The change is the final value minus the initial value. You notice that the initial and final momentum along the y direction are the same. Therefore, there is no change in momentum along the y direction. But the initial momentum in the x direction is 3i. The final momentum in the x direction is negative 3i. And therefore, there is a change in momentum in the x direction. So delta p is pf minus pi, final momentum minus the initial momentum. And we will do that for the x and y separately. What is the change in the x momentum? It will be negative 3 minus 3. Negative 3 minus 3i, that is the change in the x momentum. Plus, what is the change in the y momentum? 4 minus 4j. And that is negative 6i plus 0j. In other words, the change in momentum of the ball is negative 6 units in the negative x direction. A very important type of problem. Alright, let's do another one. A loaded dump truck with a total mass of 5 times 10 to the power of 3 kilogram traveling at 3 km per hour coasts into a loading dock and collides, coming to a stop in 0.64 seconds. What is the magnitude of the average force exerted on the truck by the dock? Well, the truck comes and hits the dock in coming to a stop. So it is the force exerted by the dock that stops the truck. Well, what is the principle we are going to use here? The truck, before hitting the dock, has an initial momentum. After hitting the dock, it comes to a stop in 0.64 seconds. So its final momentum is 0. And that will help us to find the change in momentum. The change in momentum occurred during this time. We can calculate the rate of change of momentum. And what is the definition of force we just had in the beginning of the class? Force is a measure of the rate of change of momentum. Alright, let's do that. Here we got, this is the dock and this is the truck hitting and coming to a stop. The mass of the truck is 5 times 10 to the power of 3 kilogram. Its initial velocity Vi is 3 km per hour. Convert that to meter per second. Divide by 3.6, that is 0.83 meter per second. What is this initial momentum? Initial momentum Pi is mass times initial velocity. Mass times initial velocity and that is 4,150 kilogram meter per second. What is the final momentum after it comes to a stop? Its final momentum is 0. What is the change in momentum? Change in momentum is final momentum minus the initial momentum. So delta P is Pf minus Pi. That will be 0 minus 4,150. That is negative 4,150 kilogram meter per second. Now look at this. The change in momentum is opposite to the direction of motion of the truck. Why? Because the change in momentum is caused by the force applied by the dog on the truck, which is directed in the opposite direction. That is why the change in momentum is negative. And this change in momentum occurred during a time of 0.64 seconds. Therefore, force is a measure of the rate of change of momentum. F equal to delta P divided by delta T. We have delta P is negative 4,150. Delta T is 0.64 seconds. Therefore, the force equal to negative 6.5 times 10 to the 3 Newton. This is a measure of the force applied by the dog on the truck. Watch that, it is negative. Why is it negative? Because the motion of the truck, we considered the motion of the truck to be positive. If the initial velocity of the truck is positive, therefore the force applied by the dog on the truck is opposite to that, which therefore is negative. So the negative sign simply indicates that the change in momentum is opposite to the initial momentum. Okay. Let's now talk about the concept of conservation of momentum. Remember, we talked about the conservation of energy. In the same way, we have conservation of momentum. What do you think conservation of momentum talks about? The conservation of energy tells you that the total energy always remains a constant. In the same way, if you have large number of objects that are in motion and they interact against each other, they can hit against each other, well, the law of conservation of momentum says the total momentum will remain unchanged. And that is the essence of conservation of momentum. Imagine that this room has 200 basketballs all moving about in random directions. They hit against each other. Some of the balls will lose velocity, some others will gain velocity. Suppose I measure the total momentum of the 200 balls now and leave this room, come back after a month. Some balls would have lost momentum, some others would have gained momentum, but the law of conservation says the total momentum of that system of balls will remain a constant. Now, let's take two objects to explain this. I have two trolleys here, and what happens when they interact? What is the meaning they interact? They can collide. Now, two of them are moving and they collide. Well, watch it again. What happens? Well, they have an initial momentum. Both cars have initial momentum. The action is their collision. The conservation of momentum says the total momentum before they collide must be equal to the total momentum after they collide. So if I set them into motion, there you are. Well, you noticed, let me show you this. You see, this car is at rest. If I now move the second car, watch what happens when they collide. Well, give it time for the image to settle down. Alright? Alright, what happened? Well, it did not really collide well. Watch once again. You notice that this comes to a stop and the momentum is taken over by the second one. You see, the momentum of this object is 0 before collision. This has a momentum, and what happens after collision? The momentum of this becomes 0 and the momentum is taken over by this one. This happened because these two objects have the same mass. So what does conservation of momentum say? Conservation of momentum says, in the case of a number of interacting particles, the total momentum before interaction will be equal to the total momentum after interaction. In other words, in this case we can say the total momentum before collision equal to the total momentum after collision. Watch it again. The total momentum before collision equal to the total momentum after collision. And that is the statement of the conservation of momentum. For an isolated system of interacting particles, the total momentum always remains a constant. And if you now take the case of two colliding objects, we can say total momentum of the objects before collision equal to total momentum after collisions. An object of mass m1 kilogram moving with a velocity v1i. I want you to familiarize with these notations. What does v1i stands for? Initial velocity of the first object. m1 is the mass of the first object. v1i is the initial velocity of object 1. And it collides with an object of mass m2 moving with a velocity v2i, just like the trolleys I just showed you. And after collision, the first object has a velocity v1f. Watch that again. What does it stand for? Final velocity of the first object. And the second object after collision has the velocity v2f. Well, what is the total momentum of the two objects before collision? Look at this. Before collision, the momentum of the first object is m1 times v1i. And the momentum of the second object before collision is m2 times v2i. Therefore, the total momentum of the two objects before collision will be Pi is m1 v1i plus m2 v2i. I don't know whether you can see this m2 v2i on the screen. If not, you need to write it down. So initial momentum of these two objects, Pi is m1 v1i plus m2 v2i. What is the total momentum after collision? The momentum of the first object after collision will be m1 v1f, and the momentum of the second object after collision will be m2 v2f. The total momentum after collision will be pf. Final momentum is m1 v1f plus m2 v2f. If you apply the conservation of momentum, what do you get? Pi should be equal to Pf. m1 v1i plus m2 v2i must be equal to m1 v1f plus m2 v2f. And that is what the law of conservation of momentum says. And we will use that for solving problems very often. A statement. In a closed system, the total momentum of all the objects remain the same, although collision between the objects can transfer momentum from one object to another. That's very important. Now watch an animation here. Now you have a cart that has a mass of 1 kilogram. As it passes by, you have a brick that is deposited on it. So the animation shows a cart of mass 1 kilogram moving at 0.6 meter per second. Now what is the action here? The action is the brick falling onto the truck. Therefore, let's calculate the total momentum before that action. What is the initial momentum of the, well, what do you want to call it? The cart. That will be its mass times its initial velocity. That will be 0.6 kilogram meter per second. What is the momentum of the brick before collision? The brick is at rest initially, therefore its momentum initially is 0. What is the total momentum before they collide? Will be 0 plus 0.6 kilogram meter per second. That is 0.6 kilogram meter per second. And you notice that once they collide, they move together as a single object. The total mass now is mass of the car plus mass of the brick. After they collide, suppose they have a velocity v. We don't know what that velocity is. And they have a mass of 3 kilogram. Now that means the mass of the trolley is 1 kilogram and the mass of the brick is 2 kilogram. They have a total mass of 3 kilogram. Therefore, what is the total momentum after they collide? That will be 3v. The total initial momentum is 0.6 kilogram meter per second. The total final momentum is 3v kilogram meter per second, where we don't know v. That means we can now use the conservation of momentum to figure out that v. How? Momentum after collision equal to momentum before collision, which means 3v equal to 0.6. Therefore, v equal to 0.2 meter per second. That means after the brick has been deposited, the car and the brick as a system will move with the velocity of 0.2 meter per second. Now, a principle of great application in our everyday life. Watch the two animations and discuss how the conservation of momentum is applied here. I'm not going to talk about it. Now watch this and see if there is any connection between this situation and the car and the brick. The big fish moving to the right swallows the small fish that is at rest. What happened to the speed of the combination? Now the action here is the big fish swallowing the small fish. The total momentum before collision must be equal to the total momentum after collision. That means after the big fish has eaten the small fish, the speed of the combination will be less. On the other hand, look what happened now. In the second animation, the big fish is initially at rest. Alright, there you are. And the small fish is moving. and the momentum is in that direction. That means the total momentum after collision must also be in the same direction. Momentum before collision must be equal to momentum after collision. So after collision, the system moved in the direction of the initial momentum.